We're now ready to start section 4.3 on partial derivatives. Now we've talked about limits and we've talked about continuity. The next thing we want to talk about is differentiability. How do you take the derivative of a function of multiple independent variables? Now we did take derivatives in calculus 1 of functions of a single variable. And we saw that in that situation, there were different ways to interpret the derivative. It could have been the slope of the tangent line or the instantaneous rate of change of one quantity in comparison to another. And we could also think of it as velocity if we were graphing the position versus time graph. So these were different interpretations of what the derivative meant in calculus 1. We used Leibniz's notation with the dy dx. Now, we've already seen that when you have a function of multiple independent variables, there are other issues that arise that did not arise in the case of a function of one variable. So our question now is, how do you take the derivative of a function of multiple independent variables? And the answer to that is partial derivatives. I'll share my screen so we can get started. Our learning objectives for this section are to calculate the partial derivatives of a function of two variables, and also to calculate the partial derivatives of a function of more than two variables. So perhaps a function of three variables or even four variables. Then we want to find higher order derivatives of functions of two variables and explain the meaning of what a partial differential equation is and give an example of that. We're going to start with the definition of a partial derivative. And we're going to start with functions of two independent variables. So we're in three-dimensional space, two independent, one dependent. We can think of it as x, y, z, but it could also be x, y, and time, or x, y, and temperature, or something like that. Remember from calculus 1 that we had three different ways of defining the derivative at a point. The derivative was the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Or you could replace the h with delta x and you have the same definition. You could also have called it the limit as x approaches a of f of x minus f of a all divided by a. This definition is most similar to the h definition that we had in calculus 1. Note now, however, that f is a function of two independent variables, x and y. Because it's a function of two independent variables, we have to specify which independent variable we're taking the derivative with respect to. Because it's no longer a function of a single variable, it's not clear unless you indicate which independent variable the derivative is with respect to. We use a different symbol for partial derivatives. It's partial because the function depends on two independents, not just one. We use this symbol, which looks sort of like an italicized backward 6, and it's called the partial. And we read it as the partial of f with respect to x, or the partial of f with respect to y. Notice that in the definition for the partial with respect to x, that we have the limit as h goes to 0 again of f of x plus h, comma y. The y value is not changing, minus f of xy. Note that y is the same in both terms. However, x is scooting over just a little bit, a value of h over, and then you're dividing by h. If we look at the definition for the partial derivative of f with respect to y, we'll see that it's the x coordinate, the x independent variable, that's being held constant. And instead, it's the y variable that's being allowed to vary by scooting it over from a value of y to a value of y plus k and taking the limit as k goes to 0. We can also extend that into multiple definitions, and we'll see that later on. When we talk about it, again, we say the partial derivative of f with respect to either x or y, depending on what we're looking at. In the image that you see here in the center of the screen, we have a surface in three-dimensional space. We have a point on the surface in three-dimensional space given by x, y, and the function value at xy. In other words, xy is coming from the xy plane, it's in the domain. And when we substitute those values into the function, we get a z value out. And that gives us this dot that you see to the right. Now, the idea behind the limit, of course, when we're looking in the one-dimensional case, is that as the limit gets closer and closer, the value of h gets closer and closer to 0, we get the derivative, which is the slope of the tangent line. When we look at the case in 3 dimensions, we have a secant line that cuts through the point on the surface and another point on the surface that's just been moved over a little bit. This would be varying x only by x plus h. So if x were 3, this might be 3.01. So we're just moving over a little bit. But the y value does not change. So if this was 3, 5, 10 for the ordered triple, then this would be 3.01, 5, and whatever the function value at 3.01, 5 is. So both of these points are on the surface, but they're separated by a very small amount in only the x direction. When we do this, this creates a secant line. And of course, as you might imagine, as the value of h gets smaller and smaller and approaches 0, this secant line becomes like a tangent line that is touching the surface at that one point. So you can think of the surface as kind of like my fist, and the tangent line just barely resting at that point, but in a particular direction, namely freezing the value of y and only varying the x. Let's take a look at some information that will tell us more about this direction that we have. So the slope of that secant line does represent an average rate of change of the function value z as we travel parallel to the x-axis. I've frozen the value of y, so it's not changing. In the previous example, it would always be 5, but I'm changing the value of x from 3 to 3.01. The slope of the secant line will approach the slope of the tangent line at that point, parallel to the x-axis, because the x-axis is the derivative I'm taking the partial with respect to. If I choose to change the y value instead of the x, so in my example, 3, 5, 10, I would leave x at 3, but I would vary the 5. I could make it 4.99 or something like that. I can vary it in either direction. Or I could make it 5.01. If I vary the y instead of the x, we typically say we're varying by k, and this will become the partial with respect to y instead of the partial with respect to x. Then that secant line and tangent line will be parallel to the y-axis. And as the value of k gets smaller and smaller, the secant line approaches the value of the tangent line, the slope. So the partial of the function with respect to x represents the slope of the tangent line passing through that particular point, but parallel to the x-axis. And the partial with respect to y represents the slope of the tangent line passing through the point, but parallel to the y-axis. And we'll see an example of this in just a moment in CalcPlot 3D. Let's say that we wanted to take the slope of the tangent line in a direction that's not parallel to the x-axis or the y-axis. In that case, we need what's called a directional derivative, which we'll be studying later in section 4.6. So it can be done, but it is more difficult, as you might imagine, to take the derivative in a direction that doesn't align with either the x-axis or the y-axis. the two independent variable axes. Now, there's different notations that we can use for the partial derivatives. Let's take a look at some of the more common notations that we use for the partial. You'll notice that this first notation here gives the function name, f, and a subscript of letter x, or variable x, below and to the right, sort of like we write the base of a natural log or a logarithm. And then it gives the independent variables in parentheses. F is a function of x and y, and the subscript x means that we are taking the partial derivative with respect to x. Now, we've already discussed this third representation, which is using that sort of italicized backward 6, which is called the partial of f with respect to x. It's not necessary, if it's understood what the independent variables are, to give the independent variables x and y. You could instead simply write f sub x. F sub x represents the partial derivative of function f with respect to the x variable. This will give the slope of the tangent line at a point on the surface that's parallel to the x-axis. And then, of course, we can use different notations, much like we did in Calculus 1, but with the partial notation. Now, because f as a function of x and y often represents the z value, the third component in our three-dimensional space, we can sometimes write z of x or z sub x instead of f sub x. This is similar to writing y prime instead of df dx or f prime. Y prime and f prime represent the same thing. We can also write the partial notation using the variable z in place of the name of the function f. The final part of notation we will see when we're doing the gradient and directional derivatives, but we don't use it very often other than that. It uses an uppercase letter D followed by a subscript giving the variable that you're giving the partial derivative with respect to, followed by the name of the function whose partial derivative you're taking. And of course, the second line simply gives the appropriate notations for y. If we had a function in four-dimensional space, w, as a function of x, y, and z, then we would have a similar notation, but for a function of three independent variables, and we would have then the partial of z or the partial of f with respect to z as well. Now, how does the partial derivative operate? What makes it work? The reason that it's parallel to one of the axes is because you're holding all the other independent variables constant. So you're treating the y value like a constant when you're taking the partial derivative with respect to x. When you're taking the partial derivative with respect to y, you hold the x constant. So what you're getting is how the z changes as the y value varies, but x does not vary. So how does the dependent variable change as I freeze one of the independent variables, but change the other one? This is also the rate of change interpretation again. Let's go ahead and take a look at example 1. In example 1, we want to use the definition of the partial derivative as a limit to calculate the partial derivative of function f with respect to x and with respect to y. Now, as you might expect, we don't normally use the definition. We're going to do it here as good practice to remind you that it does link back to a limit definition, but we will have a faster way of calculating the derivative, just as we did in Calculus 1. Let's go ahead and start writing down what this would represent. If I want to do the partial, oops, clicked on the wrong button, of the function with respect to x, which I could also write as f subscript x, then what I'm doing is I'm going to take the limit as h goes to 0 of f of x plus h comma y. What does that mean? Replace all x values with x plus h, but leave the y's as y. So the first term in the numerator is f of x plus h, and the second term is just f of x, which is already given for us here. And then it's all divided by, oops, I forgot to put my y's in. Too much calculus 1, comma y, all over h. Now, what does this mean? This is the limit as h goes to 0 of 4 times, replace x with x plus h quantity squared, plus 2 times x plus h times y, minus y squared, plus 3 times x plus h, I'm running out of space, minus 2y plus 5. All of that replaces the first term in the numerator, f of x plus h comma y. Then I subtract the function itself at the point that I want to evaluate the partial, x and y. So this is going to give me the 4x squared plus 2xy minus y squared plus 3x minus 2y plus 5, but all subtracted. To subtract the whole thing, we'll go ahead and change all the signs. I'm going to put this one now in a different color so that it stands out. So I get minus 4x squared minus 2xy, oops, plus y squared minus 3x plus 2y minus 5. All of this now needs to be divided by h. Now that you understand the setup, go ahead and pause the video to work out the derivative of the function f with respect to x. And if you can, go ahead and work out the partial of f with respect to y. Remember that in the partial of f with respect to y, the x coordinate stays x, but the y becomes y plus k and y. Go ahead and pause it now to work it out on your own. One thing I forgot to copy down when I did it before was the minus 2y plus 5 on the f of x plus h comma y terms. So make sure you got those written down, because otherwise it tanks the whole thing. So when we look at these, I went ahead and multiplied out the x plus h quantity squared in distributed terms. And then I subtracted the representation of the function at just generic x comma y. When you do that, you get cancellation of several of the terms, and you're left with 8xh plus h squared plus 2h times y plus 3h, all divided by h. Every term in the numerator has h as a common factor. So you factor out 1, which will cancel with the denominator and leave you with the limit of 8x plus 4h plus 2y plus 3. When you substitute h in now, this second term will go to 0, and you're left with 8x plus 2y plus 3 as the partial derivative of the function with respect to x. In other words, this representation here is giving you the slope of the derivative parallel to the x-axis at any point on the surface of this function. Let's take a look now at finding the partial with respect to y. I did this one in a different color so that it would show up a little bit differently in contrast. This time we find the limit as k goes to 0. You could use h again, of f of x comma y plus k minus f of x comma y, all divided by k. We repeat the process, but this time we're leaving the x variable as x and replacing the y variable with y plus k in the first term. When I multiply all that out and I look for like terms that cancel by subtracting the representation of the function, I'm left with the limit as k approaches 0 of 2xk minus 2ky minus k squared minus 2k all divided by k. Again, I have a common factor of k in every single term in the numerator. So I factor out one representation of k, which will then cancel and leave me with the limit of 2x minus 2y minus k minus 2. This time, when I substitute 0 for k, it's the third term that drops out, and I'm left with 2x minus 2y minus 2, which gives me the partial derivative with respect to y. Now, when I'm looking at this, what does this mean? If I take a point that's on the surface and I want to know what the slope of the tangent line is at that point parallel to the y-axis, I can plug in the x and y coordinates here and come up with something. So for example, let's just try 1, 1. If I substitute 1 for x and 1 for y, the first two terms cancel, and I get the slope of the tangent line at the point in the domain 1, 1 on the surface turns out to be -2. Now, to get the ordered triple where that tangent line touches the surface, I need to substitute 1, 1 into the representation of the function, which you see back up here. If I substitute it into the function, I would have 4 plus 2, which is 6, minus 1 squared, which would be -1, so 5, plus 3 is 8, minus 2 back to 6, plus 5 is 11. So what I'm saying is that at the point 1, 1, 11, there is a tangent line that is parallel to the y-axis, and the slope of that tangent line is -2. Let's talk about an easier way to find the derivatives rather than using the definition. We didn't use the definition very often in Calculus 1, and that's the last time we'll probably use the definition in this class. What we do instead is we hold one of the variables constant when we have a function of two variables and take the derivative with respect to the other. So we're only partially taking the derivative because we're not taking the derivative with respect to both x and y. In this case, what we're going to do is we're going to find the partial with respect to x first. And as you might expect, the partial of the function with respect to x treats every variable other than x as a constant, like 2, like a number. So when I see 4x squared, it does depend on x, which is what the differential is. So that gives me 8x for the first term. When it looks at the term 2xy, it considers the y to be just as much of a constant as the 2. And when I take the derivative, this just gives me plus 2y. The third term is minus y squared, which does not depend upon x. As you know, the derivative of a constant is 0. So the partial here will give us 0 for the third term. The partial with respect to x of 3x would just be 3. What about the last two terms? As far as x is concerned, the last two terms are also constants. So their partial derivatives with respect to x would both be 0, which gives us exactly what we obtained above, but a whole lot faster. Let's repeat the process now and take the partial derivative with respect to y. When we find the partial derivative of the function with respect to y, again, it's now going to consider y to be the variable. It's going to hold all other independent variables as constants. So as far as it's concerned, 4x squared is a constant, so the derivative is 0. And the second term, it now considers y the variable, so 2x is a constant, so the derivative is just 2x. When it looks at the third term, it takes the derivative with respect to y, so we get -2y. The fourth term is 3x, which depends on x, but not y. So when we take the partial with respect to y, we get 0. The next term will give us -2, and the last term will again give us 0, which gives us 2x minus 2y minus 2, which again is the same thing we got previously. If you will turn back to your previous work, you'll see that these solutions are identical, but this was a much easier method of doing the work. Let's practice this again. We want to take a look at example 3, where we're going to take the partial with the faster method, not the slower one, and then we'll do it again in example 4. Now in example 4, notice that this is W written as an equation that depends on x, y, and z. So when we take the partial derivatives, because it has 3 independent variables, we'll need 3 partial derivatives. That would be the partial with respect to x, the partial with respect to y, and the partial with respect to z. Go ahead and attempt examples 3 and 4 on your own, then turn the video back on so we can compare our answers. Make sure when you're doing these that you apply the chain rule. So let's take a look at example 3 first. In example 3, we want to take the 2 partial derivatives of the function of 2 independent variables, x and y, given by tangent of the quantity x cubed minus 3x squared y squared plus 2y to the 4th. The derivative of the outside function tangent is secant squared. We freeze the inside and don't change it from the original. Then we have to multiply by the derivative of the inside. In this case, the partial derivative, first with respect to x, then with respect to y. So both of these will have the secant squared of the original inside of tangent. The partial with respect to x will be multiplied by 3x squared minus 6x y squared. If your professor wants, you could factor out a common factor of 3x, giving you the line that's highlighted in yellow here. For the partial with respect to y, you'll have the secant squared of the original argument to the tangent multiplied by -6x squared y plus 8y cubed. And again, you could factor out a common factor from the second set of parentheses of 2y. You can never factor anything out of the argument to a trig function. It's good practice to leave the trig function at the back to make it clear that this part at the front is not a part of the argument. I also make it clear when I handwrite them by putting dots in between to show it's different. You could also use big square brackets to show that as well. Again, what we're doing is we're holding one of the variables as if it were a constant while we take the derivative with respect to the other. This is what's known as the partial derivative. Let's now take a look at example 4. In example 4, we have a function of 3 independent variables, x, y, and z. W is equal to the cosine of the argument x squared plus 2y minus the exponential e raised to the 4x minus z to the 4th y power. And then we have a plus y cubed term at the end. There are 3 first-order partial derivatives, the partial with respect to x, with respect to y, and with respect to z, corresponding to the 3 independent variables. When we take the partial with respect to all of these, we're going to get a term of negative sign x squared plus 2y, or rather a factor, because the derivative of cosine is negative sign, and we freeze the inside. The partial with respect to x then multiplies by the derivative of the inside, but with respect to x only. That makes the 2y term become a constant term, so its derivative is 0, and the derivative of x squared gives us 2x. When we look at the exponential, it does have the variable x in it, so it does depend upon x. When we take the derivative of an exponential, we get the exponential times the derivative of the power. The derivative of 4x minus z to the fourth y with respect to x is just 4. What about the third term? Well, a y cubed doesn't have x in it, so the derivative is just 0. This gives us a final value for the partial with respect to x of minus 2x, sine of the argument x squared plus 2y, close the argument, minus 4 times the exponential raised to the 4x minus z to the fourth y power. When we take the partial with respect to y, it considers x and z to be constants, but allows the y to be the variable. In this case, we still get negative sine of x squared plus 2y, but now we take the derivative of the inside with respect to y only. That's going to give me a 2 added onto that factor. When I take the derivative with respect to y of the second term, I get the exponential again, no change, times the derivative of the power with respect to y. The 4x doesn't depend on y, and the second part of it does, so I get a minus z to the fourth. The last term does depend on y, so I get a 3y squared. When I take the partial with respect to z, it considers both x and y to be constants. Notice that the original trig function cosine depends only on x and y. In that case, z considers the whole thing to just be a constant, and the derivative of the constant is just going to be 0. The exponential depends on z, so you take the derivative of that, but the third term does not depend on z, so you ignore that. We now want to talk about various ways of interpreting the partial derivative. In Calculus 1, we interpreted the derivative as the slope of the tangent line, the rate of change of one function with respect to another, and as the velocity function when we were graphing position versus time. In this case, we have slightly different interpretations of the partial derivative. We've already seen one interpretation in that if you fix y and take the partial with respect to x, we can get the slope of the tangent line at a point that's parallel to the x-axis. Let's take a look at some other interpretations. One of them is as increasing versus decreasing. We're going to take a look at this hyperbolic paraboloid that you see here. The hyperbolic paraboloid, of course, looks like this, sort of a saddle shape, I guess you could call it. Let's take a look now at an example of this. What happens as we approach the point 8, 5/2, 63 over 4? Now, 8 5/2 was chosen more or less at random, and you can find the value 63 over 4 by substituting 8 and 5/2 into the equation in place of x and y and solve for z. This gives us the value of z of 63 divided by 4. So what we're asking is z increasing or decreasing with respect to x as the point xy approaches that ordered triple? Is it increasing or decreasing with respect to y as the point xy approaches that ordered triple? In other words, let's interpret the partial derivative with respect to one variable or another as indicating whether or not the dependent variable is increasing with a unit change of that variable. Let's take a look at what it looks like now. We're going to go ahead and we're going to take the partial derivative of our function with respect to x. So we'll start with respect to x. This is going to give me the partial of z, or f, with respect to x, which you can also write as z sub x. And the partial, of course, would consider the second term in the equation to just be a constant, and the derivative of x squared divided by 4 would give me a 1/2 x. Now I want to evaluate that at the particular point I'm interested in. At that point, is z increasing or decreasing as x varies by one value, 1 unit? So now I'm going to evaluate the partial with respect to x at the ordered triple 8, 5/2, which is 2.5, and 63 divided by 4. In this case, the only thing to plug in is the x coordinate, and I get 1/2 of 8, which gives me a value of 4. Now 4 is positive. Because it's greater than 0, this means that z is increasing. Increasing how? Z increases by 4 units for every positive 1 increase in x, by 4 units for every 1 increase of x at that point. So this is another way of interpreting the partial derivative. We're predicting that as far as the x is concerned, as we increase the x value by 1, the z value goes up by 4. Now, let's go ahead and take a look at this on the actual function in CalPlot 3D. So in CalPlot 3D, I entered the equation here in the z equals, and then I opened what's called the 2D trace plane. The 2D trace plane is the third icon below the main icons, and it's the third graph type icon. When you click on that, it's going to drop down a 2D graph, which is projecting a point in the plane. We can also then click on a menu that shows up to the right once that's opened. When we click on this, scroll down to where you see Show f sub x trace tangent line. Now we're looking at this right now. What is this doing? Let's take a look now at the graph. It's a little hard to see because the colors aren't contrasting well. So I'm going to click on the function for the surface, the hyperbolic paraboloid, and reverse the colors. Let's now take a look over here at what we have. When you look at the image, you should see the actual point here in blue. How do you set the values of the point? Come over here to the slider bars or enter it into the boxes that the x value is 8 and the y value is 2.5. And it tells you up here that that becomes 15.75, which is 63 divided by 4. This blue dot is our ordered triple. We want to know at that point, is the z value increasing if I increase x by 1? If you increase x by 1, you're moving in this direction. And as you can see from the picture, the z value is increasing quite rapidly. So it's going up by 4. The tangent line is here in black. So as it goes up, the other goes up. Now, if we come down here and we take a look, I'm not sure what it would do if I graphed it. No, I guess it does not. I was hoping it would show it to me in 2D, but I can click on this in 2D. Now, when I click on the 2D symbol, do you see how that partial derivative, which was graphed in red, is parallel to the x-axis? The partial with respect to x is parallel to the x. And you can see it here as this red line parallel to the x. Let's go back to the 3D image. This red that you see right here is the partial derivative of the function with respect to x, which is itself, of course, a function. If you want to see how it changes as x changes, you can slide it along that curve, and you can see the tangent line moving. What if you were to change the y instead? If you change the y instead, then you're moving with respect to y, but it's still giving you the partial with respect to x for that fixed value of y. Let's now go back and compute our partial with respect to y. when we look at the partial with respect to y, we're going to again take the partial derivative of the function equation. The first term will go to 0, and the second term will give us negative 2y divided by 25. So the partial of z with respect to y is equal to negative 2 over 25 times y. Now we want to evaluate that, the partial with respect to y, at that ordered triple, 8, what is it, 2.5, 15.75, or you can use the fraction form. This means that I'm substituting 5 halves, or 2.5, in place of y. This would give me negative 2 over 25 multiplied by 5 over 2, which is going to reduce to give me a negative 1 over 5. This value, of course, is less than 0, which means that z is decreasing by 1/5 for every positive 1 change in y. 1/5 units for every positive change in y. Let's take a look now at CalcPlot 3D and see how to look at that point. So again, we want to return to the value of 8, 5 halves. So we can enter 8 into the X box and 2.5 or 5 halves into the Y box. We'll hit enter so that it moves. However, it's still graphing the partial with respect to X. Notice how it would sort of, if you project it into the plane, be parallel to the X-axis. Let's click up here on the drop-down menu next to the 2D menu board and select Show F sub Y Trace Tangent Line. Now you can see it right here. Notice at this point that the line does have a negative slope, but it's relatively small. It's not nearly as steep as the partial with respect to X. When we're looking at this, of course, is tracing it as we vary the value moving across. When we're looking at this trace is going to be parallel to the y-axis, which is running in this direction. You can see that by clicking on the 2D menu. And you can see here that the tangent line is parallel to the y-axis. And if you use your mouse scroll bar, you can barely see the red poking out of the end, which of course is the function which represents the partial derivative with respect to y. And again, you can see how it changes at different values of x and y if you want to move it that way. Let's now go ahead and take a look at another interpretation. Keep in mind that, as in the last example, it is entirely possible for z to be increasing with respect to x while it's decreasing with respect to y, and at different rates. We saw that in the previous example. Let's now look at the view of the slope of the tangent line, which was the first view we took in the first example we did. Remember that the trace of a surface is the cross-section created when the surface intersects a plane parallel to one of the coordinate planes. So it's sort of like an image of an intersection of two surfaces. The partial derivatives are the slopes of these traces. So the partial derivative with respect to x at a particular point, a, b, in the domain, is the slope of the trace of the function when it intersects the plane y equal b. Now, why would it be the plane y equal b? When I do the partial with respect to x at a particular point, remember that we hold the y variable constant. So y remains b, which means that I'm intersecting the plane y equal b. So if this was the partial of x at the point 1, 5 in the domain, which is the xy plane, then I would have the intersection with the plane y equal 5 at the point 1, 5. And the partial derivative with respect to x would be the slope of that trace at that point, which is what we talked about in the first example. The partial derivative with respect to y allows y to vary, which means that it's going to intersect with the plane at x equal a. And this would be at the point a comma b. This way of interpreting the partial derivative says that the partial with respect to x is the slope of the tangent line through the point xy f of xy and is parallel to the x-axis when projected into the xy plane. This is the same thing that we've seen in CalPlot 3D. Let's take a look at a picture, and this will make it a little bit clearer, I hope, right? So this is coming out of the notes from section 4.1, where we had two surfaces, a function g of x and y given by negative x squared minus y squared plus 2x plus 4y minus 1, definitely a quadric surface, and the plane y equal 3. We wanted to see what the intersection of the two was. What is the trace when they intersect? Now, since g was already solved for z, the dependent variable, we chose to let x equal t since y is always going to be 3. Y is a constant, so we let x be the parameter. We wrote it as a parametric equation by choosing x equal t, y staying 3, and then we substituted x equal t and y equal 3 into the expression for the equation of g. And this gave us negative t squared plus 2t plus 2. And we graphed this as a space curve r of t in CalPlot 3D. Let's go ahead and take a look at that now. So you'll see it's going to look like this. And let me click over to the next one so you can see it. There it is right there. Here is our, let me see if I can get the x to disappear. There we go. You can see that I've got the plane there where y is equal to 3, right on the value of 3. And I've got a paraboloid opening down, and the trace is that yellow curve in the center. The yellow curve is given by the parametric equation here. And you could change colors and make it something different, but yellow contrasts rather well with the sort of pink purpley color and, well, not so well with the green. All right, so we've got this interpretation here. Now, the partial derivative is going to be the slope of a tangent line on the yellow at a particular point where they intersect. So let's take a look at the next part. We're going to find the partial derivative, which is the partial of g with respect to x. Coming back up to our function, which is right up here. Let me highlight this in yellow so you can see it. When we're looking at this, if I take the partial with respect to x, I get negative 2x plus 2 minus 1. All right, negative 2x plus 2 minus 1. When we come down here, then we have, well, let's see, it looks like I didn't write it down. So, that's a problem. Let me go ahead and write it down. This would be negative 2x. What did I say? Negative 2x plus 2x plus 2. And that would give us that value there. And then, of course, what we're doing is we're going to find the slope of the tangent line at a point. At what point? Well, we know that the y value is 3. We don't know what the x value is. So you can substitute 3 in place of y, which will give you this negative x squared plus 2x plus 2, which is basically what we had up above in terms of t. And then let's just choose an arbitrary point. This is totally arbitrary. The first one was set, y equals 3, but now I'm being totally random, and I'm going to choose x equal 3. If I substitute that in here, that will give me the ordered triple 3, 3, negative 1, which has to be on my surface. So it has to be on my surface somewhere, and you can see it pictured here in yellow. So let's come across to the next image, and you can see that's my point right there, which is at 3, 3, negative 1, and it's on my surface. You may be wondering, well, how did you get it on the plane? Well, hang on and I'll show you. Once I have that 3, 3, negative 1, I know the trace in the plane where y equal 3 is a 2D curve. So it's got to have a tangent line at this point, 3, 3, negative 1. What's the slope of that line? I went ahead and computed the partial of g with respect to x. How did I get a -1 before? That must have been an error. Oh, yeah. I don't know where the -1 came from. That's what happens when you're trying to go from one page to another. The function should have been -2x plus 2. Yes. There, much better. Okay. So when we're looking at this, nice to know professors make errors too, right? Okay, so when we're looking at this, the partial derivative with respect to x is given by that function. That would be at any point, all right? Now, the next thing I want to do is evaluate it at the particular point I'm interested in, which is on the plane where y equals 3, because I set y to be 3 and just randomly picked x as 3. When I substitute this in, I get -4. This means that the value of z is decreasing by 4 for every +1 increase in x, which means that 4, 3, -5 has to be another point on the tangent line. And you can see the tangent line drawn here with the y kind of taken out of it. Now, the green plane that you see here is not the plane, or I guess it is the plane where y equals 3, since y is coming straight out at you. And it's that plane. Let's go ahead and take a look at this one out there on the space. So we've got that, we've got this here. And now you can see where we've got the plane where y equals 3. We've got the trace where it intersects that paraboloid. We've got the point 3, 3, -1, and now we've graphed the tangent line right here. Now, how did we graph the tangent line? And this one is an actual graph. I could get it, of course, by doing the trace with respect to x and then substituting the coordinates 3, 3 as we did before. But there's a way to find the actual equation of the tangent line. So what we're going to do is we're going to replace our function g as a function of x and y and represent it as a vector valued function. So basically all we're doing here is just rewriting it as vectors so that the endpoints of those vectors produce the curve. So this gives me r of x and y as x equal to x, y equal to y, and z equal to the original value of g. So this makes it a vector valued function. When I look at that vector valued function, I want to take the partial derivative with respect to x. The partial derivative of this vector valued function will give me 1, 0, -2x plus 2. Note that the -2x plus 2 matches what we got when we directly took the partial derivative of g with respect to x. This is the vector valued function. Now, why do I need a vector valued function? To give the equation of the tangent line, I need a vector in that direction and a point. I already have the point 3, 3, -1, but I need a direction vector. This vector valued function, the partial derivative of it with respect to x, will enable me to calculate what that vector's direction is at the point 3, 3, -1. So I take 3, 3, -1 and substitute it in the partial derivative of r with respect to x. There's only the x to substitute in, which gives me the vector 1, 0, -4. when I'm looking at this, again, x was 3, so that gave me -6 plus 2, which gives me -4. So it goes through the point 3, 3, -1 in the direction of 1, 0, -4. Now, how can I plot that information? Again, what we want to do is create a space curve, a vector valued function, but not of 2 variables this time, just 1 variable, a parameter t. So what we do is we write r of t, not the same r of x and y as before, as the position vector of the point, the vector 3, 3, -1, plus a parameter t times the direction vector 1, 0, -4. The t allows it to run back and forth as much as we want. In CalcPlot 3D, you'd probably want to choose at least -10 to 10 to get enough of the tangent line. So coming out here and looking over here, you can see that we have written 3, 3, -1, 1, 0, -4, and this represents the tangent line. And you'll notice it's going from -10 to 10. This would line up with what we would get on the trace with respect to x if we clicked on the 2D trace plane menu. That's the third one that looks like a graph, a 2-dimensional graph. And let's click on the downward opening menu, select Show FX Trace Tangent Line, and we chose, I believe, 3 and 3. Y had to be 3, and we just selected 3 for x at random. And you can see that it is now lining up. So it's kind of hard to see. It's sort of in there kind of tight, but it is in there, right? The blue is in there with the black. Let's see if I can take the blue off for just a moment so you can see. Oh, no, it took everything off. My bad. Okay. So if I move it a little bit, let's see if it shows up a little better. If I move it a little bit, it shows up better. I don't know how that got changed too. There we go. And this needs to be at 3. All right. So we've seen a way of representing the function as a vector valued function of 2 independent variables, which we've not done before, in order to take the partial derivative of it with respect to one of the independent variables, and then substituting a value in to get the direction vector at a particular point. Then we can take the point and the direction vector to create a line. And that line is the tangent line at that point in the plane y = 3. Let's now go ahead and look at what it looks like with a contour curve. Now, the contour curve we've seen before, you're going to click on the contour plot symbol, which looks like 4 sort of concentric circles on the graph. So when we do that, coming over, I believe, to the next one, you can see it here. To get the contour plot, you want to click on this symbol here, which looks like the red circles down next to it, and didn't quite click. We want to evaluate it at that particular z value. Our ordered triple is 3, 3, -1, so I set the first level value to be -1. I'm really only interested in what happens right there, so I just tell it I want one contour plot, and then I can click on Create Plot, and it's going to plot a red level curve. Notice here that the blue line, which represents the tangent line, and the yellow, which represents the trace, in the plane y = 3 are both parallel to the x-axis. The tangent line is the slope of it is the partial derivative with respect to x. We're holding y constant, and so this is coming through right there, parallel to the x-axis at the value where you got it, y = 3. Remember that clicking back into the graphing region will show you the contour line on your particular plot. It sometimes has trouble remembering to keep plotting the point. So you may have to put the point back on, but then you can see it all. Let's take a look at another example. We want to find the slopes of the traces to an ellipsoid 10 minus 4x squared minus y squared equals z at a particular point in the domain 1, 2. And then we want to write the equation of the tangent line at that point. So we'll need to represent our function as a vector valued function of both x and y. The first thing we need to do is we need to compute what the ordered triple is there. So we need to find z at the point in the domain 1, 2. If you replace x with 1 and y with 2, you should come up with a z value of 2. That gives you the ordered triple 1, 2, 2. This is the point at which we want to find the equation of the tangent line. So we're looking at that right there. We want to find the slopes of the traces at that point. Let's take a look at our next step. There are going to be two traces, one in the x direction, one in the y direction. If you're taking the partial with respect to y, you hold x constant. Our point was, what was it, 1, 2, 2? I think that's right. Let me go back up and make sure. Yes, 1, 2, 2. So if I'm taking the partial with respect to y, I hold x constant in the plane x equal 1. So I'm looking for where the ellipsoid or paraboloid is going to intersect here, not ellipsoid, paraboloid is going to intersect with the plane x equal 1. This will be dictated by the partial with respect to y. If I'm doing the partial with respect to x, I hold the y constant, in this case, the plane y equal 2, and this gives me a different intersection with that paraboloid. Let's take a look at the two intersections right now. Here's the first one, which you can see right here, and it's intersecting with the plane where x equals 1, and it looks like that. And you can see the point 1, 2, 2 right here in pink. The other one is going to be intersecting where y equals 2. So you can see that the plane is at the y value where y is constantly 2. And it produces a different trace, in many ways narrower than the previous trace. This one was sort of more spread out. And that's because of the nature of the paraboloid, right? Now let's go ahead and take a look at what it looks like. Let's do the work to find the traces and find the equation of the tangent line. The first thing we want to do is find the equation of the trace between the plane x equal 1 and our paraboloid. Let's go ahead and come over here so we have some room to work. If we are intersecting the paraboloid with the plane x equal 1, then in our equation for the paraboloid, which is 10 minus 4x squared minus y squared, we can replace the x value with 1, giving us 10 minus 4 minus y squared. Then we can parameterize this as a space curve, r as a function of t, by selecting y to be the parameter t. Because this is also intersecting the plane where x is always 1, the x value will be 1, the y value will be t, and the z component will be 6 minus y squared. When you plot that, you will get the yellow trace of the intersection of those two 3D surfaces. That will give you the yellow that you see here. Once we have that, we want to find the slope of the tangent line and the equation of the tangent line at a particular point. The particular point we found to be 1, 2, 2. Now that we know how to graph the trace, we want to go ahead and compute the partial derivative. So the next thing that we're going to do is we're going to compute the partial derivative of z with respect to y. Coming back up to our equation again, which is written up here, 10 minus 4x squared minus y squared, the partial with respect to y would be negative 2y. Now we want to evaluate that at our particular point. So this tells us that the partial with respect to y evaluated at our point 1, 2, 2 would turn out to be a negative 4, which means the z value is decreasing by 4 at that point as y increases by 1. Now, the next thing we need is we need that vector valued function in order to get the direction vector for the tangent line. So we're going to rewrite z, but in terms of a vector valued function r of x and y. Let's go ahead and rewrite the equation so that we have it here. Our equation that we're basing all of this on is z equals 10 minus 4x squared minus y squared. So the next thing that we want to do is we want to represent it as this vector valued function of x and y, which means that x and y, well, stay x and y, and z becomes 10 minus 4x squared minus y squared. To get a direction vector, we take the partial with respect to the same variable we did just a minute ago, which is the y variable. So we're going to take the partial of r with respect to y. When we take the partial of r with respect to y, we get 0, 1, and negative 2y. The next thing we need to do is evaluate that at our particular point. In this case, we want to evaluate it at 1, 2, 2. So evaluating that partial derivative at 1, 2, 2 leads us to the direction vector 0, 1, negative 4. Notice the negative 4 matches what we got for the partial derivative of z with respect to y. When we look at it this way, this gives us a direction for the tangent line, and we have a point 1, 2, 2. So now we represent the tangent line as a space curve. The tangent line is going to be written by r of t equal to the position vector of the point 1, 2, 2 plus t times 0, 1, negative 4. You could write it as a combined equation, r of t equal to 1, comma, 2 plus t, comma, 2 minus 4t by adding together the corresponding components. This gives us the equation of the tangent line at that point in the tangent or in the plane where x equals 1. When we do this, it is going to be parallel to the y-axis, and you'll see it down here, parallel to the y. And you can see here our graph of the trace and our graph of the tangent line in the directions. Let's go ahead and take a look at that one now. I think, is that this one? I believe that's this one. Yes, this one. 1, 2, 2, 0, 1, negative 4. All right. And that gives you this one right here. And again, if we want to see that the trace and the tangent line are parallel to the y-axis at that point, we can go to the original function of the paraboloid, click on the contour plot symbol, which it seems to always take 2, select the z value at that point, which is 2, plot one contour plot, and then click on create plot. When you do, it will switch to the 2D image. Notice that this is here at the value where x equals 1, and it is parallel to the y-axis. You can see the trace in yellow barely coming out here at the end, and the blue is the tangent line. Now that we've done it with respect to y, go ahead and pause the video and rework the entire process, but with respect to x. And turn the video so we can compare our results. Okay, let's see how you did in doing the same process and finding the tangent line that's parallel to the x-axis by taking the partial derivative with respect to x. The first thing we want to go through is just to find the equation of the trace, that is the intersection of the paraboloid with the plane where y is equal to 2, holding y constant, allowing x to vary. So again, we start with our equation. We replace the y variable with 2, which gives us 6 minus 4x squared. We can parameterize this as a space curve by allowing x to be the parameter t and setting the y value at the constant 2 and letting the z component be z minus 4 times t squared. That will give us the graph of the intersection of the plane that you see here with the paraboloid. And we can look at it over here. Oops, looks like I clicked off of it. Where did it go? Rats. I think it's this one right here. It will give you the other value that you're looking at right here, which would be that yellow curve. That's the trace. And now what we're trying to find is the tangent line at a particular point. So when we're coming over here, once we've traced out that, we want to evaluate the partial derivative of the function with respect to x. So our function is again 10 minus 4x squared minus y squared. So the partial with respect to x is negative 8x. And at our particular point, 1, 2, 2, that will give us negative 8. So the z value is decreasing 8 units for every positive 1 increase in x. We've already represented this as a vector valued functions of 2 variables over here on the left when we did the partial with respect to y. Now we want to take the derivative of this, but with respect to x, which would give us 1, 0, negative 8x, where the 1 represents, well, the derivative of x is 1, and the derivative of y with respect to x is 0, and the derivative with respect to x of z is going to be negative 8x. Plugging in our point gives us a direction vector for the tangent line of 1, 0, negative 8. Then we can write the tangent line as the sum of the position vector for the point 1, 2, 2 plus t times the direction vector 1, 0, negative 8. We can combine corresponding components and represent this as the space curve 1 plus t, comma 2 minus 8t. And that would give us the tangent line representation, which I'm trying to remember where it is. I've had several open, so I've kind of lost track, but there it is right there. All right, so you can see it. And it does lie within that plane, or actually that may be the wrong one. Y equals 2. Is that the right one? Yep, this is the right one, where y equals 2. All right, and you can see the point right there. All right. Now that we've worked through what is really a fairly difficult problem, we want to take a look at a second or third way of viewing partial derivatives. Now, I don't require my students to do this very often because I don't find it as helpful of a view of the partial derivative, but I do want to cover it because it is another way of thinking about the partial derivative, and that's using the contour map. So we could approximate the partial derivative at a point by finding the slope of the secant line connecting 2 points using contour maps. And you'll find an example of this in your textbook. This method, however, is difficult at best when one of the coordinates is 0, when both x and y are non-zero, it becomes quite difficult. It's not really practical. So again, we won't use this very often in the course, but we will work examples 7 and 8 just to show what we were doing. Now, in example 6, we found the partial with respect to x evaluated at 1, 2 to be -8. And now we want to approximate the partial with respect to y of 3, 5 using this contour diagram right down here. So we're looking at this. This is a contour map. And remember that along these blue arcing curves, the value of z is always the same. So if you walk along the contour line, you're not changing the z value. It doesn't go up, it doesn't go down, it stays constant. These are labeled 6, 8, 10, 12, 14, 16, 18, and 20 as you move from the right to the left, coming out towards the larger ones on the outside. We want to evaluate what the partial derivative is with respect to y at 3, 5. So in this case, we're allowing the y to vary by a little bit, but we're leaving the x alone. All right, we're going to keep the x constant. So the partial is approximately equal to the difference quotient. All right, that's the slope of the secant line. So the one on the left, the partial with respect to y, is the actual slope of the tangent line. What's represented on the right side is the slope of the secant line. So we have a couple of ordered pairs that we can find off of this graph. And again, at the bottom, it's a little hard to see, but the label down on the horizontal axis gives you the x values, and the label on the vertical axis at the far left gives you the y. So you can locate the 0.35 by moving out here, so along the x = 3 line up to 5. So right there at 3, 5, we have that the contour line, the value of z is 14, roughly, more or less. And then if we move up along the x = 3 line, because we're holding x constant, taking the partial with respect to y, it's approximately at 3, 7, it's approximately 16. It's actually a little bit lower than that, but it's close to 16. Now, how do we approximate the slope of the tangent line with the slope of the secant line? Well, we just use the difference quotient. So we take the difference in the z values at those 2 points, 16 minus 14, and we divide by the difference in the y values. So from 7 to 5 is a difference of 2, and that will give us 2 divided by 2, which is 1. Now, this, of course, is not a great approximation. Note that we could have also come down and used whatever it is down here at about 3, 3, which would have been about 12. We could have used that as well, and we could average the two results maybe to get something slightly more accurate. Let's take a look now at example 8. So in example 8, we're taking a look again at the same curve that we did in example 6. This is 10 minus 4x squared minus y squared at the same point 1, 2, 2 on the surface. So we want to approximate what the slope of the tangent line is at that point. So when we're looking at this, this again is just giving us the image of the contour line at that particular point, and also the intersection of the paraboloid with the plane. Now, on the first contour curve, we're going to use c = 2. That means z is 2, since that's our point 1, 1, 2. So x = 1, y = 2, and z = 2. To find the second contour curve, we want to adjust over just a little bit. Say maybe x equals, I don't know, 1.5. But we're going to leave the y value constant at 2. All right, we're taking the partial with respect to x. So, and then we can find the z value by substituting this value, 1.5 for x and 2 still for y, into the equation for z. And this gives us a z value of -3. This gives us 2 points that are definitely on the surface. And to approximate the slope of the tangent line at the point 112, we can instead use these 2 points to get the slope of the secant line, which is close to that tangent line. So this represents the point 1.52, -3. And then we find the slope of the secant line by subtracting the z values and dividing by the difference between the x values, so 1 minus 3/2. And this gives us about -10. Now, this isn't a great approximation, all right? It's not fantastic. How could we make it a better approximation? Well, don't move so far over. If the x value is 1, instead of moving to 1.5, maybe just move over to 1.01, much closer to that point. If we do that, then when we approximate the slope of the tangent line with the slope of the secant line, we get something much closer. Remember, the actual slope at that point for the partial with respect to x turned out to be -8. And when we just move over to 1.01 to, and whatever that came out to be, 1.9196, then we get -8.04, which is a very good approximation. Let's take a look at finding partial derivatives of functions of more than 2 variables. Now, this is essentially going to be exactly the same as finding a partial of a function of 2 variables. It's just that instead of only the 2, you do have a third one as well. So suppose you have a function of 3 variables, x, y, and z, and you want to find the partial of the function with respect to x. Then again, you allow the x to change just a little bit from x to x plus h, but you hold y and z constant, and you take the limit as h goes to 0. We have the similar definition for the partials with respect to y and with respect to z. With respect to y, we allow the y to change just a little from y to y plus h, taking the limit as h goes to 0, but we hold x and z constant. And of course, the partial with respect to z, we hold x and y constant and allow z just to vary just a tiny bit, and then take the limit as h goes to 0. Let's take a look at example 9, where we want to find all of the first partial derivatives of this function of 3 independent variables. So we're in 4-dimensional space. Again, remember that you're going to have to apply the chain rule. Derivative of the outside function, which is trig in both terms, leave the inside function alone times the derivative of the inside function. Go ahead and pause the video now to work out the 3 first partial derivatives, then turn it back on so we can compare. So let's compare our answers. For the partial of this function of 3 variables with respect to x, we get 2xy times secant of x squared y times tangent of x squared y. The derivative of secant is secant tangent, minus secant squared of x cubed yz squared, all multiplied by 3x squared yz squared. And I was kind of lazy and didn't put those at the front like I should have. When we do the partial with respect to y, we're holding x and z as constants. This derivative of secant will again give us secant tangent with the same argument as the original, x squared y, multiplied by the derivative of the original argument, but with respect to y, which gives us x squared. On the second one, the derivative of tangent again gives us secant squared with the original argument, multiplied by the derivative of the original argument with respect to y, which is x cubed z squared. When we take the partial with respect to z, we're holding x and y as constants, which means the first term, which has no z in it, is a constant. And the derivative of a constant is 0. The second term does have a z in it, so the derivative of negative tangent is negative secant squared. Looks like I've got my negative out front, my secant squared with the same original argument inside, multiplied by the derivative of the original argument, but with respect to z, which would give me a 2x cubed yz, then multiplied by the secant squared. The next thing that we want to talk about, since so far we've only been taking first partial derivatives, is can we do more derivatives? Can we take the derivative of the derivative? And the answer is yes, you can. It becomes more complicated than in the case of a function of one variable. We have to indicate each time we take the derivative which independent variable we're taking the derivative with respect to. You cannot use prime notation for partial derivatives because prime notation doesn't indicate which independent variable you took the derivative with respect to. You'll see down here that there are different notations, and we'll learn another one as well based on the function name with a subscript. Let's go over the first, which is Leibniz's notation. We have the partial squared of f divided by the partial of x squared. Well, first off, it's not really divided. This isn't really a fraction. This is an operation which represents the second partial derivative of the function f with respect to x both times. And that's really how you ought to say it. The second partial of the function f with respect to x both times. When we're looking at this, what we're actually doing is taking the partial with respect to x of the partial of f with respect to x. That's what it means here in the yellow highlighted box. In the second one, we have the second partial of the function f with respect to y both times. This represents the partial with respect to y of the first partial of f with respect to y. All right. Notice that when you write it in sort of this second form, that what gets done first is what's inside the parentheses, and what gets done second is outside the parentheses. So the order is not left to right, it's actually right to left, which is counter to the way that we read in English. This is what's found in the blue highlighted box. Let's now take a look at the purple highlighted box. When we look at the purple highlighted box, we again have the second partial derivative of the function f. However, when we look at the bottom, notice that it has different partials in the bottom. This indicates that we're taking a partial with respect to y first, and then with respect to x. It's read from right to left because it represents the second notation you see here, the partial with respect to x of the first partial with respect to y. The partial that occurs second is actually done first in Leibniz's notation. Then we have the last one, which I've not outlined in any particular color. It's also the second partial derivative of the function f, but this time we take the partial with respect to x first, and then the partial with respect to y second. Now, the question you should be asking yourself is, are the last two the same? And the answer is no, not always. There are occasions, there are conditions under which they are the same, and we'll be learning about those shortly. There's another notation that we can use for these that can make it it makes it a little more complicated, I think. We can write it with the function name or z or w, whatever the dependent variable is, with the subscript notation. However, in this case, you read the subscripts left to right, not right to left. So when we look at the one on the second row, f sub yx, this represents the partial with respect to y first, then the partial with respect to x. And you can see it written in Leibniz's notation next to it. The partial with respect to x and then with respect to y is written in this format as f sub x y. Again, in the subnotation, we do it in the order that it's written. In Leibniz's notation, we do it in right to left order. Remember that the partials with respect to x and then y, or with respect to y and then x, are not necessarily the same thing. Order does matter. Let's take a look at example 10. We want to calculate all 4 second partial derivatives for the function below. In order to do that, we'll have to find the first partial derivatives first, and then find the second partials. The second partials are the partial of f with respect to x both times, the partial of x with respect to y both times, the partial of f with respect to x and then with respect to y, and the partial with respect to y and then respect to x. Go ahead and pause the video to work these out, then turn it back on so we can compare our results. So let's take a look. In order to find the second partial derivatives, I first find the first partial derivative with respect to x and the first partial derivative with respect to y. I color-coded them so that the one with respect to x is in blue and the one with respect to y is in pink. When we want to compute the second partial derivative of the function with respect to x both times, we're taking the partial with respect to x of the partial with respect to x, which would be this expression in blue. So this becomes the same. When we take the partial again with respect to x, we get -9 sine of the argument 3x minus 2y minus cosine of the argument x plus 4y. We apply the same process to find the second partial derivative with respect to y both times. In this case, we need the first partial with respect to y, and then we take the partial with respect to y of it again. And this will give us -4 sine of the argument 3x minus 2y minus 16 cosine of the argument x plus 4y. Again, what we're doing is we're taking the partial derivative with respect to y after we've already taken the partial with respect to y one time. So we're doing it twice. And this is represented with f sub yy and the Leibniz's notation. Let's take a look at what's called a mixed partial derivative, where we have a partial with respect to each variable that's independent. In the Leibniz's notation, remember it's actually read left or right to left because what's in parentheses gets done first. So we're applying the partial with respect to x after we've taken the partial with respect to y. So the partial with respect to y, of course, is this value that you see up here, which is the same as what you see here. Then, however, we take the partial with respect to x, and we get 6 sine of the argument 3x minus 2y minus 4 times cosine of the argument x plus 4y. When we do the other mixed partial, where we have the partial of the function with respect to x followed by the partial with respect to y, or f sub xy, then we represent first the partial derivative with respect to x, and then we take the partial of that with respect to y. Notice we get exactly the same thing as the other mixed partial. So the question is, what condition caused this to happen? When are the mixed partials f sub xy and f sub yx the same, and when might they be different? Let's take a look at what's known as Clairaut's theorem. Clairaut's theorem gives us the condition under which those mixed partials are going to be continuous. So what does it say? Suppose that our function of two variables is defined on an open disk D that contains the point AB. If the second mixed partials, f sub xy and f sub yx, are both continuous over that subset of the real plane, then they must be equal to each other. So what is this saying? This is a rare situation where continuity does imply differentiability. That does not occur in a function of a single variable. In a function of a single variable, just because it is continuous does not mean it's differentiable. Think about the absolute value function with a corner at the origin. In that case, it's not differentiable at the origin, but it's definitely continuous there. Clairaut's theorem gives us a condition under which continuity of the mixed partial second derivatives does give us differentiability, all right, and does tell us that they're equivalent. So when I'm looking at it, and I'm looking at this right here, I know that 3x is a continuous function because it's polynomial. So is minus 2y. It's also polynomial. Sine is a continuous function. A constant times a continuous function is continuous. X plus 4y is a continuous function. Cosine is a continuous function. 4 times it is a continuous function. And the derivative of continuous functions is continuous. So f sub yx is continuous. And since f of xy is the same, they have to be equal to each other. If they're both continuous, they'll be the same. This does make it much easier to determine when they're going to be the same by determining whether or not those second mixed partials will be continuous functions. We have one last item that we want to discuss, which is a partial differential equation. Now, this is a calculus class, not a differential equations class. There is an entire course, one semester long, that looks at how to solve partial differential equations. We've seen previously in Calculus 2 an ordinary differential equation, which involved y, y prime, y double prime, possibly the independent variable x, combinations of those. For a partial differential equation, it involves an unknown function, we're trying to find the function, of more than one independent variable and one or more of its partial derivatives. So it might include the independent variables, it might include multiple ones of the partial derivatives. Here are some of the more famous equations that are partial differential equations. The heat equation in 2 dimensions gives us u sub t equal to c squared, where c is a constant, times the quantity, the second partial derivative of u with respect to both times, x both times, plus the second partial of u with respect to y both times. So this is an equation that relates to partial derivatives. And again, we could write this in Leibniz's notation as follows. This would give us the partial of u with respect to, say, t, would give us c squared times the second partial of u with respect to x both times, and I'm running out of space, plus, oops, I've got my parentheses in the wrong place. Let me move that over. The second partial of u with respect to y both times, right? Now, let's take a look at an example of a partial differential equation. In example 11, we simply want to verify that u, which is a function of x, y, and t, given by the equation 2 sine of argument x over 3 times sine of argument y over 4 times exponential e to the negative 25t over 16, we want to prove that that's a solution to the heat equation, which you see here. So let's go ahead and take a look at how we could fill this out and how we could find out if it's a solution. Remember, if it's a solution, it should satisfy the equation, which means that we need to find the partial of u with respect to t to replace this part right here in the equation. Then we'll need to find the second partial of u with respect to x both times to replace this part of the equation. And finally, we'll need to find the second partial of u with respect to y both times in order to replace this part. Then we'll add the two second partials together, multiply the result by 9, and check to see whether it's the first partial of the equation with respect to time. Go ahead and pause the video to work this one out, and then turn it back on, and we'll look at our results. In order to prove that this u is a solution to the heat equation given here, we need to find each part. The partial of u with respect to t turns out to be -25/8 sine of argument x over 3 sine of argument y over 4 times exponential e to the -25t divided by 16. Let's now take a look at the second partial of u with respect to x both times. In this case, we take the partial with respect to x after we've already taken the partial with respect to x once. When we do it twice, we get -2/9 sine of argument x over 3 sine of argument y over 4 times exponential e to the -25t divided by 16. When we take the second partial of u with respect to y both times, we get -1/8 multiplied by the same factors as we found in the second partial of u with respect to x both times. In other words, the only difference between these two is the constant at the front. Then we set this equal, possibly, to the first partial of u with respect to t. When you do that, notice that they're all constant multiples of the sine of x over 3, sine of y over 4, e to the -25t divided by 16. That means that we can ignore that part and just focus on the constants. So this really becomes proving, of course, that these two multiplied by 9, which was in our heat equation, does turn out to be -25/8. And in fact, it does turn out to be -25/8. This is the end of this particular section on partial derivatives. It can be rather difficult to find the equation of the tangent line, as we saw earlier, but actually computing the partial derivatives is relatively straightforward by comparison. In our next video, we'll take a look at tangent planes and an equivalence or an analogous thing to the linear approximation function that we studied in Calculus 1. See you soon.